So we're now going to go on and look at question number 3 from the 2025 paper. This is where the difficulty really starts to pick up. So you should, especially if you're in year 13, you should have been able to do most of question 1 and 2. And if you're in year 12 and you're sort of taking this process seriously, you should have looked ahead at some of the concepts that usually come up that you might not have covered so far in the course. Maybe you haven't done Hess's law, but you probably should have looked ahead and had a look at that. Similarly with some of the organic chemistry and unit cells, although unit cells wasn't on this paper. Now, question 1 and 2, question 1 was 8 marks, question 2 was 9 marks. If you're doing reasonably well on here, that's probably got you most of the way towards a silver, because that's 17 marks altogether. So, maybe you got 13 or 14, maybe you made a mistake with the Hess's law part of question number 1, or maybe you couldn't quite work out how to do the half-life part of question number 2. That's fine, but if you get most of these, you pick up a few more marks here, you should be getting a silver. If you're going for gold, you really need to be maxing out the marks on this one, and then looking to, because if you get 17 on these two, then really all you need to do is get about 15 on the remaining 4 questions, so about 4 marks per question, and that will take you to a gold. So we're now going to move on and have a look at question number 3. So this is about epoxides, which you may or may not have come across. It has been asked before in previous years, and it can be quite interesting. So, state the general formula of an epoxide that contains N carbon atoms. There's a couple of ways to work this out. It does give you 4 examples, so you could just work out what the formulas of these 4 examples are, and then sort of do it from there. So, this one here is obviously going to be C2H4O. And most people will have covered skeletal formulae before they do the Olympiad. If you haven't, it's definitely something that you want to do, otherwise the majority of the organic chemistry just will not be accessible to you. And then we can see that any time you substitute onto the carbon here, like I've done here with a CH3, so this is a CH3, what I've done is I've taken off, obviously there's 2 hydrogens here, I've taken off one of those hydrogens and replaced it with a CH3. So if I take off a hydrogen and put on a CH3, that's the same as adding a CH2. So I've taken off a hydrogen, so I've taken off that hydrogen, and I've added a CH3. That's the same as adding CH2. Okay, so any of these is always going to differ by the addition of CH2. So it'd be C2H4O, C3H6O, C4H8O, from which we can deduce that the general formula will be CnH2nO. And you can go back and you can convince yourself that all of these will follow that general formula. So then we have the approximate CCO bond angle for the following molecules, and we're asked to do, we're given the same table in the question paper and in the answer booklet. So C2H5O, C2H5. This is an ether, so we should be fairly comfortable that what we're looking at for this here is going to be this molecule. Alright, so I've got my 2 carbons, 3 hydrogens here, 2 hydrogens here, so that's C2H5. Now, the CCO, so it's going to be CCO. So if that's a hydrogen and that's a hydrogen, obviously this is an sp3 hybridized carbon atom. So our tetrahedral bond angle 109.5, nice and easy. And then we've got this. Well, it's a triangle, so it's going to be 60 degrees. There's not really much else to say about that. It can't be 90 degrees. I know you can get a 90-degree angle in a triangle, but if the CCO is 90, then this CCO can't also be 90. Alright, you can't have 2 right angles in a triangle, and it is symmetrical, so it has to be 60 degrees. Okay, alright, now that's the easy part done, so that's 3 marks, and if that's all you get on this question, that's pretty good. You can probably pick up 1 or 2 other marks, because this is when it starts to get a little bit more tricky. So we're given this common way of making epoxides from this organic peroxy acid and the alkene. And we have the mechanism here, and you probably won't have seen any mechanisms like this unless you've done a lot of very thorough preparation. But you always just remember that the curly arrow, and you can see here that they've obviously had a little bit of trouble drawing this curly arrow, but that doesn't matter. It takes the electrons from this bond and attaches them to that carbon. So what's happening there is this oxygen is going to bond to that carbon. So this arrow here corresponds to the formation of this bond. And then the electrons in the double bond go through this carbon atom onto the oxygen. So this arrow here corresponds to the formation of that bond. And then we've got the other stuff going on up here to make A. So what's happening here, we can see that the R doesn't really do anything, and the electrons in the double bond between the carbon and the oxygen, they go and form a bond with hydrogen. So my carbon oxygen is no longer going to be a double bond, but the oxygen is now going to be bonded to hydrogen. And then my oxygen here, so that's my hydrogen sorted out because it's out here, this oxygen becomes this oxygen here, and then the electrons in this oxygen-oxygen single bond then go back into the carbon-oxygen bond, so that then becomes a double bond, like that. Alright, so that's our other product, so we just go ahead and write that out. Okay, there you go, nice and easy. Alright, now, a little bit of stereochemistry. So, it can be added either from the top or the bottom. Now, if it's symmetric, it's probably just going to give you one isomer, and if it's asymmetric, it's probably going to give you two isomers. So, what are we asked to do? We are asked draw the structures of both stereoisomers formed when propene reacts with a peroxy acid. Okay, so propene. Alright, in that case, let's keep our schematic diagram here, which gives us very nice instructions. And propene, we can actually just draw it out here. So if I just draw the same thing, but I do it as propene, it's going to be a hydrogen and a hydrogen. I'm not going to draw the stereochemistry there because it's irrelevant, because they're both the same. And then it's going to be a hydrogen there, and then because it's propene, it's going to be CH3. So all I've done is it's that thing. They're the same thing, but I've added the hydrogens in, and I've sort of rotated it round so that the methyl is coming out of the plane. And then you can see quite easily, all you need to do is just add the oxygen on, or just redraw this, but replace R1, R3, R2 with hydrogen, and R4 with the CH3. So let's just do that here. So I'm going to get hydrogen, hydrogen, CH3, hydrogen. And then I can do the same thing here. Remember, the R4 is the only one that's going to become a methyl. So that's hydrogen, 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 CH3. Okay. Now those are my two stereoisomers. That is the answer to part D. All right. And you should be able to convince yourself that those two are not the same molecule. If I take this and I flip it over like that, I rotate it round, the oxygen is going to come up to the top. Nothing's going to happen here because these are the same, but my methyl is going to rotate round to the back. Alright, so what I'm going to do is, in my answer booklet, I'm going to draw them out. I mean, I would be fine if you drew them out like that. I wouldn't have any complaints about that. But I'm going to draw them both sort of with the oxygen pointing up. So I'm going to have my first one, no change. And then I'm going to rotate this one up to give me, obviously nothing happens there, but this CH3 that's pointing out of the paper here is going to be pointing into the paper. Like that. Okay, so those are my two isomers. Okay, so now we move on to part E, where we're asked to deduce the number of isomers formed from each of the four following. Number one, very easy, because all I've done is I've taken the propene and I've replaced it with butene. So before, this was just a CH3, it just ended there. Now it's just gone one further. There's no reason for that to be any different to propene. So straight away, I'm just going to put 2 in there. And you can draw it out if you want to convince yourself, but you'll find that it's like that. Now we get a little bit more tricky. So if we do it like this here, what's going to happen? Well, I'm going to end up with my 2 possible isomers being, this is where I'm going to need some scrap paper. So you should, when you do the test, you should have a piece of scrap paper. It does say in the instructions that you're allowed to have a piece of scrap paper. So I'm going to take my scheme here and I'm going to apply it to this, which I can redraw as this, okay? And then you'll see that all I'm doing is R3 and R4 are the 2 methyl groups, so I get this isomer with my hydrogen, methyl, methyl, hydrogen, and I get this isomer. So again, it's always the R3 and the R4, so those 2 are sticking out. Okay, so those are my two, you can't quite see that. Those are my 2 isomers that I'm getting from this alkene here. Okay, so the question now is, are these the same or are they different? Well, it should be fairly clear that if I take this molecule and I rotate it around like that, you will get the same molecule. All right, so these 2 are the same. So in my, that's my, oh, I ticked on the wrong thing, there we go. There's Man's booklet. So those are the same, okay? So you can spend a little bit of time looking at it, but that one I think is fairly straightforward. So the next one is this. Okay, so this is now the trans alkene. So if I do the same analysis again, all right, so this now in a sort of the representation that you're given in the question looks like this, with your CH3, CH3, H, H. So you can do the same analysis and you will get, now I get the CH3 back here, and my H down the front, CH3 at the front, H at the back, and then if I do the other one, this is very rough, so I get my H at the back, CH3 there, H at the front, CH3 there. Now, the question is, are those 2 the same as each other? Do the same thing again, take this one, rotate it round, you'll find that the CH3 here ends up here. And this CH3 rotates back to give me that one. All right, so if I rotate this round, what I'm going to do is take this one, rotate it round, I'm going to get this. Okay, so these two are the same, but are these 2 the same? Okay, and you should be able to see that there's nothing you can do to these to make them the same, because if I rotate it around like that, yeah, around the axis of the pen here, the CH3 here is always going to go back to the CH3 there. I'm never going to be able to return that. So there, that's going to be 2 as well. All right, and then I have my last one, and the last one should be fairly clear that if I have that, I'm just going to end up, I'm not going to go through the whole thing here, I'm going to get that, and then my other one is going to be that, and those 2 are definitely the same. So yeah, that. Okay, alright, so moving on, we are now on to this reaction of the epoxide with a nucleophile. And we're given 3 different reactions and we're asked to draw the structures of B, C and D. So you have the general mechanism here, or the general reactants and products that you get. So what's happening here, we can sort of think it's just like a ring opening. So the nucleophile is going to come in, hit that carbon, open up the ring. So then the nucleophile will be bonded to this carbon, that's that carbon, which is bonded to this carbon, that carbon, and then the alcohol forms over there. All right, so if we do that, the thing you need to do is just recognize that the nucleophile, so which atom is it going to bond through. So it's always going to bond through the one with the lone pair of electrons. So essentially all I need to do is just replace my Nu here with my S, and obviously the hydrogen comes off. They've made that pretty clear here. The hydrogen comes off, and I've also got a methyl there. So I can draw that on here. So my B is just going to be my HO, like this, HO, and then my S, and then that is going to be bonded to my CH3. Okay. Then I do the same with ammonia. This one I think is even easier. So I just replace my Nu with my NH3, but obviously I lose a hydrogen and I make the alcohol. So I'm going to get my HO, and then it's going to be NH2, like that. Okay. And now D is a sort of tricky one because it says a third equivalent. And you have to think for a little bit what that means. What does it mean to have a third equivalent of NH3? It's sort of, if you've not seen this kind of thing before, you think, well, a third of this reacts with that? Well, that doesn't make a lot of sense. What makes more sense is one of these reacts with three of these. Okay, so here I've done a one-to-one reaction. Okay, but if you think about it, in this product here, I've still got a lone pair of electrons on my NH2. So this goes ahead and reacts with another one. All right, so what I get is I have my epoxide, and then I've got my product from part C, my NH2OH, and then I get this reaction again. All right, so I will still have my first one, and then I get another one, and it's 3 to 1, so I also get a little bit funny angles, but there you go. That'll be your third one. Okay. All right. Then we have a particularly useful epoxide. It's called epichlorohydrin. Sodium phenoxide reacts with epichlorohydrin to form an intermediate anion E-, which then cyclizes, forming product F. So we have this. Now it should be fairly clear that this here is going to be your source of the electrons. This is going to be the nucleophile, and it's going to come over and it's going to react there and break that bond. Now it is possible that this could come here and break that bond, and you might want to draw out what you would get from that reaction. The correct answer is the one that I've shown. Now I'm not an organic chemistry expert by any means, so the preference assumed here, perhaps it's most likely to be a steric influence, this group being in the way, but there could be some sort of electronic effect that I haven't that I might have overlooked, but this is the one that we're going to be looking at. So if we do that, it should be fairly clear that we're going to have our benzene ring, and then our oxygen, and then you just need to be really careful. So your oxygen bonds to this carbon, which bonds to this carbon, which bonds to the alcohol. Okay, so I'm going to have one carbon. So this carbon here, and then another carbon. Those two carbons are these two carbons. And then I've got my alcohol. Or in this case, it's an anion, so that's where the electrons are going to be. And then this carbon here, this carbon is also bonded to my CH2Cl. Like that. Okay. And then it cyclizes, and the cyclization is just going to be that the electrons here are going to come down and kick out the chlorine. That should be fairly obvious because you can see that the difference here, C9H10O2Cl becomes C9H10O2. So we just lost the chlorine. Right, and that happens, just the electrons from here come down here. So what I can sort of draw that out. So you have this O minus, I'm not going to bother drawing that out, Cl. All that's happening is this is going to come down here, and that's going to come off there. And you're going to have a 1, 2, 3 membered ring. So it's going to be and then you just got to make sure you draw it properly, like that. Okay, all right. And then we get to the last page of this question. So we are now onto part H, and we have this epoxy plastic reaction scheme. Alright, so we have our concentrated nitric acid, concentrated sulfuric acid. Very, very common reaction. So this produces the nitronium ion, which is used for electrophilic electrophilic substitution of benzene rings for nitrobenzene. So it's worth just knowing that if you have those reactants, that is what you form. If you didn't know that, I mean, it's if you didn't know that, it's less likely that you'll know this, but it's always possible that you recognise this as a reducing agent, and the reducing agent is producing the amine, so, well, this being reduced is going to produce an amine, fine. But anyway, then we have our H. So what's that going to be? Well, you're given the molecular formula, always very helpful. So here, the molecular formula for this is C6, H, 1, 2, 3, 4, 5, 6, 7, N. And the only change that I've got is I have lost 2 hydrogens. Take a guess. It's probably going to be those 2 because there's no change to anywhere else in the ring here. And I've added a nitrogen. All right, and it's an ion, so this is going to be Cl. Well, it's an ionic compound. So this is the Cl minus. This is going to be a positive thing. All right, so I'm just replacing my 2 hydrogens here with a nitrogen. So draw that out. It's going to be N2, and then you need to have the positive charge on there as well, like that. All right, and then we have to work out I. So we take this and we react it with this to make this. Now here I've got 6 carbons. Here I've got 15 carbons. And this has got 3 carbons in it. So let's have a look. Does that make sense? 6 plus 3 is 9. So I'm short another 6. So it's going to be 2 of these reacts with 1 of these, and you can see that obviously in the final product I've got 2 benzene rings, so it's definitely going to be 2. And that's the kind of, I know it's for some people might think, well, that's obvious, why is he going through that? It's just that's the kind of checking and the approach that you want to have to this kind of thing. Check the molecular formula, check this product, check the final product, see if it all makes sense. So then you can start to think, right, well, the benzene ring goes to the benzene ring to benzene ring. This carbon is going to be that carbon, and then these 2 carbons are going to be these 2 carbons. So in other words, what's happening is we're getting, this is coming in here, doing that, does the whole reaction, and then another one comes in and adds to the same carbon center. All right, so let's just go ahead and start drawing it, and then we can just sort of stop when the molecular formula gets to C15H16O2. So we just draw the start, that's that, and I draw my benzene rings in. Ooh, a little bit messy. So what have I got there? 6, 12, 13, 14, 15. And then so at this point I realise I've actually made a mistake. I could go back and edit it, but I think it's probably worth just leaving it in so that you see that people do make mistakes in these kinds of things. It's a pretty obvious mistake that I should have spotted. Obviously this can't happen, because if this were to happen, and I imagine some of you have probably noticed this before I did, if this were to happen, then there would be an additional oxygen between my benzene ring and my carbon center in here. All right, but this oxygen is this oxygen down here. All right, but I was double checking. I got to the point where I had enough carbon atoms, and then I realized I didn't have my oxygen atoms. And I thought, well, hold on, if the oxygens are sticking out down here, like they are here, then it can't be happening like that. So it must just be electrophilic addition again from the benzene ring. All right, so sorry about that. That's obviously not what's happening. What's more happening, that can stay. What's more happening is this is just coming out and doing that. Alright, so that's not a problem, because if I just add on my alcohol groups there, that should now give me my correct molecular formula. 6 and 6 is 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alright, so that is my final structure for I. Right, and you can see that that then is just going to go ahead and do the reaction that we've already covered back up in step F with the addition of this epoxide. All right, so hopefully that didn't confuse anyone too much. I think I confused myself more than anybody else. But let's carry on to the final part. H, draw the structures. Nope. Badge, so this thing, reacts with a hardener to form epoxy. The repeating units of some epoxides are shown. All right, so you've got the example and then the two that you have to work out. Classic Olympiad style question will show you one, and then you have to work out the other ones. All right, so you should be able to, by looking at this one, with a bit of effort, work out what's going on. So if we just take a little bit of time to look at our example, just so we're clear what's happening. Because there are a couple of ways you can do this. You could sort of just work backwards from this and try and work out what it is, or you can do it by analogy. So if I look at this one, look at what's different about the polymer between these two, and then apply that to what's different about these two. Because it looks like this is going to be fairly closely related to this. So what I've got is I've got my carbon here. All right, so this carbon is going to be this carbon, okay, and then this carbon is going to be this carbon. Then I've got my N from here, and then I've got this carbon and this carbon, which are the two carbons in the diamine, and then I've got the sort of same thing at the other end. All right, so if I come down and look at this, I've got the same sort of thing, right? So I've got this carbon and this carbon, which are going to come from my epoxide. Then I've got the first of my NHs, okay, just like I've got the NH here. And then I've got the two carbons, which I had here. I had a carbon here and a carbon here. And then my next N. But then I've got this extra bit of chain. All right. So what I've got, more or less, is I've got my NH2. N with a methyl on. Then I've got another two carbons. And then that's bonded to this N. And that's got a methyl on it. And then I'm bonded to this one, these two. And then that's the one with the H on. That's the one that reacts with the epoxide. So I get that. All right. So if we then think about it, let's double check and make sure this makes sense. Because here, in this amine, diamine, I've got 4 atoms. I've got 1, 2, 3, 4. And you see I get 1, 2, 3, 4. All right. But in this one, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? Double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let's double check this in. How do I do it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it doesn't quite add up. I must have made a mistake somewhere. Let's have a look. So, N, carbon, carbon, N, carbon, 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 N. Ah, here we go. So, I got that one. I didn't include that one, so let's get that. Let's just rechange that to that. H2N. Alright, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this molecule. I mean, obviously I've got this methyl here and this methyl here, but they're not part of the chain. So I've got 10. So let's go back and count. These two, remember, are from the epoxide, so I don't count those ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would make sense. All right, now that's kind of a, I mean, it makes sense to me. For you, hopefully it's not just confusing you. If it is, maybe go back and have another look at it. But that is our J. So we have H2, N, like that. Yeah. Make sure you don't make that mistake, which is very easy to make. And H2, like that. All right. So then let's look at the last one. Now, what they've done is been a little bit sneaky, because I can just immediately count. So if I see these first 2 carbons come from my badge molecule, I can then look at how long my my hardener needs to be. So here it was 4 atoms long, here it's 10 atoms long. So let's have a look. Ignore the first 2, just like I'm going to ignore these 2 here. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it comes back to the badge molecules in the epoxide. So this is also 10 long. But what they've done is they've shifted. Remember, with a polymer, you can shift this wherever you want. I can move this bracket back to here, right? As long as I then take this one. So I put the bracket here, I then put this N over here, and the bracket here extends. You can put the brackets wherever you want, as long as it makes sense, right? So what they've done is they've sort of shifted the bracket all the way to here. All right, so then I've got my COH, COH, and then my C, C, and then they go into the next repeating unit. But it is the same thing, because here I have nitrogen, 2 carbons, nitrogen, 2 carbons, nitrogen, 2 carbons, nitrogen. And that's exactly what I've got here. Nitrogen, 2 carbons, nitrogen, 2 carbons, nitrogen, 2 carbons, back to here. So I know immediately that it's going to be roughly the same as this. Whoops, I didn't look at my N there. Always double check your work. H2N, N, N, NH2. But the difference is what group is on these middle 2 ends. Here it's just a methyl group. Okay, it's getting a little bit messy now, but there's just a methyl group there. Whereas now what they've got is another 2 carbons and another amine, which then can do these sort of, I don't know what the correct term is, interchain links or something or other, but it is obviously just that. All right, and as you can see, that's actually symmetrical, so it would be equivalent bonding through that one or that one. You know, so they've drawn the polymer chain going like this, but obviously the polymer chain could be going, you know, in some other direction as well. All right, so I mean, I don't know much about epoxides, but I imagine this is probably pretty tough. But there you go.